Hi, this is a video about ionic compounds. We're going to learn how to name and write the chemical formulas. So, forming ions, metals tend to have 3 or less valence electrons, and if they lose them, then underneath they'll have a full octet of electrons like a noble gas. Nonmetals will have 5 or more, so they're really close and they just need to gain a few more to get up to having that full octet. So we have something called cations and anions. Cations are positive ions, so the metals form cations. I have a way to remember this. So this is a cat, and there's the positive. So the cation is positive, or positive, like a paw. Anyways, and then anions, you can think of a negative ion. So there's the word anion. So cations, metals tend to become cations. They lose and become positive because they now have more protons than electrons. Anions are going to be the nonmetals. So it's important that you know then, and I think we've covered this, but just to double check, that you know where the staircase is. And I don't know if my staircase is quite lining up, but I think this is where I want it. So everything to the left is a metal. Everything to the right, so there aren't many, is a nonmetal. Also, poor little hydrogen, all by himself, but he's also a nonmetal. So another thing we can do is we can look at the electrons, the valence electrons, and then we can tell what type of ion they're going to form. So group 1, remember they're all S1. They just need to lose that 1 electron. So when they do, they become positive 1. Group 2 all ends in S2. They just need to lose those 2, plus 2. The D block is not as easy to predict. Group 13, some of them are positive 3. Group 14, another one that we don't necessarily can't predict. They can do a lot of different things. But then we get over here, like group 15 is S2P3. So it just needs to gain 3 electrons. So that would make it negative 2. These group 16 are S2P4. They just need 2 more. Group 17 is S2P5, just needs 1 more. And then these noble gases are not going to have or form an ion charge. The other ones that always have a certain charge, nickel and silver and zinc. So the nickel, we're going to say, is always plus 2. Zinc is always plus 2. And silver is plus 1. These are on the back of your pink mole map. But, you know, so you can always look them up. All right. So compounds, when you see a compound like, for example, Prozac, the antidepressant, anti-anxiety, it tells you the elements, so we know there's carbon, hydrogen, fluorine, nitrogen, and oxygen, but it also then tells us how many. So the subscripts are telling us relative to each other. So I have 17 carbons for every 18, I know you can't read it through there, 18 hydrogens. For every 3 fluorines, 1 nitrogen and 1 oxygen. So that's what a chemical formula shows us. So naming ionic compounds, when we name an ionic compound, we want to name the first part, or the metal. It's usually the metal. Sometimes it's the polyatomic ion NH4+, but the positive goes first. So for example, if I have a compound down here, calcium chloride, I'll bring it over here just so you can see it a little better. So I would just name calcium normal. But then the anion, the nonmetal, that's where I'm going to change. Instead of chlorine, I'm going to chop off the ene, the ione, and I'm going to add ide. So I brushed my teeth this morning with sodium fluoride. So all of those nonmetals, oxygen becomes oxide, sulfur becomes sulfide when they're in a compound. So we're talking about the ion. There are multivalent metals, and these metals are metals that can have more than one charge. One thing I would do on your on the back of your pink mole map, this is called your ion chart, I would cross out the Latin. We're going to just name using the Roman numeral system. So, but you can see as I'm doing that, these are the metals that can have more than one charge. Like chromium can be +2 or +3. So then I would call this one chromium. It's still a cation, so I don't change the ending. And then Roman numeral 2, that matches the charge. This one would be chromium Roman numeral 3. So you do have to remember your Roman numerals. 1, 2, 3, and then there's also 4. Remember, 4 is the 5 minus 1. So when you do have a multivalent metal like this one, you have to figure out which lead that is. So we're still going to call it still the cation, still lead. And then sulfur becomes sulfide. But the question is what's the charge of the lead? So what I do is I go back and I know that sulfur is right here. So I know sulfur is -2. So if I know this is -2 and I know that compounds are electrically neutral, then I know this lead must be the +2 kind of lead. And if I go back here, I can see, well, there's a couple I forgot. Lead is either +2 or +4. So it is the +2 kind. There's also polyatomic ions. We talked about these before, but we'll talk about them again. So the polyatomic ions, like here's acetate. It's, you know, they have a bunch of, or at least 2 different kinds of elements covalently bonded, but overall they have a negative, most of them are negative charge, except for ammonium is positive. So you don't, when you're writing formulas for these, you keep them together. They literally are bonded together and don't come apart. So you don't want to change their subscripts. Like SO4 sulfate. I don't want to change that 4 because then it's not sulfate any longer. So when I name the polyatomic ion, also, not only do I not change the subscripts with the ion, I name it exactly how it's found on the ion chart. So here, whenever you have 3 or more elements, you have to figure out which part is the poly, and you're going to get better with that with time. So the ClO is my poly, and then sodium's my cation, so I'm just going to name sodium. I don't need a Roman numeral because it's not one of those special metals. And then ClO is somewhere hiding on me, right here. And that's called hypochlorite. So I don't change the name, I name it exactly how I find it here. Here's another, and the polys are easier to see when they're in parentheses. So this is going to be lead, and we're going to have to figure out which lead it is. So I'm going to leave that for the Roman numeral, and then SO4 is sulfate, which is somewhere again hiding down here. So notice that the sulfate is SO4 -2. And if you have 2 of those, then you have a -4 charge. So that means that your, just wait now, is that right? +4. Yeah. That means that your lead would have to be 4, +4. Because if this is +4, and then you have these 2, then overall you would add up to a neutral charge of 0. So writing chemical formulas is similar but different. You still put the cation first. If you do have a Roman numeral, that's the cation charge. You're going to be balancing charge, so we want to make sure everything is electrically neutral. Once we balance charge, we check our subscripts. If they are reducible, we do. And then the polyatomic ions, like I was saying, we don't change their subscripts, but if we need to, we put them in parentheses with a subscript on the outside. So here's some examples of writing the formula. So here I have lead, and it's +4 because of the Roman numeral 4. Sulfide is sulfur, which is going to be in this column, so it's -2. So if I balance charge there, you can see that I would need to have 1 lead for every 2 of these sulfates, so that would then add +4 and -4 would be 0. So it would be PbS2. Sometimes we do the crisscross method, where if you take the superscript charges, the +4 and the +2, or the -2, just the number, not the charge, and you bring it down to the opposite ion, then you would get Pb2S4. So if you do that technique, then you would know that you need to reduce this, and then you would get this. But the reason you're doing that is to balance out the charge so it adds to 0. Another example here, sodium sulfate. Sodium is in that column, first column, so it's +1. Sulfate, we just saw on our polyatomic ion chart, or our ions, that it's -2. So I'm going to need 2 sodiums. I can bring that 2 down. I can also just see that I would need 2 of these for every 1 of these. One more, aluminum is +3. It's in group 13. Acetate is on my pink ion chart. So this one now, I'm going to need to have 3 of these. And I don't want to change the subscripts because then it changes what the ion is. So what I'm going to do is I'm going to say aluminum, and then I'm going to write my acetate, and I'm not changing anything about it. But then I'm going to put a parenthesis around it with the 3. Because they're negative, I would need 3 of them to balance the charge of the aluminum. I want you guys to pause and try these, and then we'll do them together. All right, so here's calcium sulfide. Calcium is +2, sulfide is sulfur, so you have to go backwards. And then to balance charge, our formula would be CAS. This one here, now I'm going to name cation first, barium. And then I need to find this on my pink ions, and that's called phosphate. So I don't need to say how many, that I have 3 and 2 in my name at all. The barium does not need a Roman numeral either because it's in group 2. Tin 2 chloride. Tin means it's +2 because of the Roman numeral 2. Chloride is chlorine in group 17, which is -1. So this would be SnCl2. I think we did this one, but this is going to be lead, and then something, and then sulfate. So I would look, and I know that sulfate from my chart is -2, and I have 2 of them. So that means this has to be the +4 kind of lead. And then lastly, I've got chromium +3 because of the Roman numeral. Nitrate is NO3 negative. So I'm going to crisscross, or I'm just going to think, okay, that means I need 3 of this guy. So I'm going to come over here, NO3, parenthesis 3. Here's a worksheet that you guys are going to be doing. I want to just show you how it works. Like here, I would match these 2, but put the cation first. And I would need 2 of these to balance charge.